Good afternoon, everyone. So I would like to mention that Joachim actually came by bicycle. So yeah, that deserves a bit of applause. Okay, so yeah, so I would like to acknowledge all the people who are working on in situ data. In situ is a very fundamental component of the observing system. And it's in the whole observing system, it's more like the bicycle, actually, right? It will still working. It will still keep working. But it does require a significant amount of work all the time, and this is why we have so many contributors. I'm not sure how we advance the slides here. Ah, okay, thank you. The in situ data go back a long time, and this is why they are very fundamental for our understanding, but that's not the only thing. They are still the only provider of useful information for several key essential variables, essential climate variables like pressure at the surface or precipitation over land. And they're also very useful if you want to project information from the satellite data into useful geophysical understanding. So this is why we still keep funding, our people keep funding in situ networks for all those aspects, and also in situ keeps going and growing and becoming stronger because it's adopting similar techniques of the spatial. So in situ is as strong as it's ever been, and I think it will still keep growing. And in fact, if you're looking at how data are used in the IPCC report, this is the last one. You can look at the Annex 1, which is a very comprehensive annex telling you what data sets have been used. And looking by the taxonomy in situ remote sensing, which was done by the authors, and looking at the essential climate variables, you can see the precipitation and air temperature at the surface are the most key variables people care about. I'm not saying the others are not important, it's not what I'm saying, but those are the first two, and that's because they really influence people's lives and how you can grow food. But there are many, many variables that are needed, and for many of them, in situ is still the only provider. So, and if we look at how in situ is supporting the C3S products, like reanalysis, we can use a time machine, which is reanalysis, go back to 1979. Here it's just a random date, it's July 15. And we can compare how good are the various generations of reanalysis that ECMWF has produced, all the way back to FIGI, era 15, era 40, era interim, and now era 5. And we can see how much better it's getting each time. Now, of course, because this ratio is up to 1, you can imagine at some point, yeah, okay, fine. But we'll never get there because there is more information to be gathered, and also we are able to filter out more of the noise. If we use that same time machine and go back to 1940, 1941, so back then, the observing system was actually even more sparse, and this was the beginning of a global war. It was not completely global until the end of 1941, but already data exchange was dropping, and data collection was becoming much more difficult. And if we look at the accuracy of our analysis today, if we compare with our fellow producers from NOAA, for example, we can see that ERA 5 is still doing the best job among all of these at reproducing the observation variability. This is for all the variables that surface marine networks can observe, from the surface wind, direction, temperature, dew point, pressure, and SST. So today what C3S is doing is delivering data sets of in situ data, which have been gathered by many other people. We're not actually collecting measurements ourselves. But what we are doing is delivering the data on the web, making it understandable in a shape that looks and has the same feel across the data sets. And that's to improve the level of service so people can compare things across, and they can use them directly without having to do a PhD in a specific topic. So they can still do the PhD, but okay, fine. So the first lot has delivered something very interesting, which is a data rescue service. So this is about bringing to the attention of everyone the fact that when there are some paper records, it is worth looking at them to see if they exist in digital archive. If they don't, then maybe they have some value. So this is helping with crowd sourcing, if you wish, but also getting the attractivity and the attention of the fact that those environmental records are of a high value. The other 4 contracts in the first phase of C3S have delivered data sets. So I will just pick on a few of them. I will start with that one here. It's an example of data sets over Europe, high-resolution grid data sets. For each data set, they have about the same look on the web. You have a visual, you have a digital object identifier, which is a persistent resource, which is telling you data will remain there for a long time. And then you have a number of variables that it contains. And then we have usage statistics, and if we look at the in situ data sets that are published on the data store, you can see the usage varies, and also the number of ECVs that it covers. So for the next phase of C3S, the current one now, the idea was to revisit the way the contracts were set up and organize this in a more modern way of taking stock of the fact that the observing system is a tiered system of systems. At the top of it, you have the reference networks, very high quality, but very few stations. And then as you go down, you get more stations, but probably the quality goes down. So this is how those contracts have been arranged. There is one which has to do with the comprehensive networks for surface, land, and marine. And this one is progressing. I will show an example of data over Africa. That's a car. Yeah. And the second one is accessing data from the baseline, the reference networks. So this one is more diverse. You have to, the contractors talk to many different parties. It also reaches out to atmospheric composition because it has a very important say on the climate evolution. So there are key variables that will be looked at. And then the third one has to do with the high resolution data over Europe from which is what KMI is working on. So the evolutions are listed here. I do not have the time to go through all the details, but in a nutshell, it has to do with rationalizing the work that is being done and improving the user experience and integrating the data. So an example of rationalization is documentation. Documentation is something that, unless you look at the data, you probably don't care too much about it. But documentation is something that typically used to be done in the form of fixed format documents, as the name says. But now we moved on to something which is much more fluid, referenced, still referenced, and it's simply a web-based type of documentation. So like this, when there are user queries coming back and saying, oh, we found this problem, it's very quick to update the documentation and also alert the users. These are the key points you need to watch out for, much faster than having the previous cycle of updates. Integration of data sets is another example. If somebody is interested in a given variable, he shouldn't have to look for 5 or 6 different data sets to figure out which data set is the right for him. So this is what is going to happen in this lot, integration of types of data sets which are similar or connects. They will be merged together and they will have the same shape. Another aspect of rationalization is a data model. So a data model is how you represent the data. And so a great deal of thinking was done in the previous phase to come up with a single data model. And this is very different from the approach in the US where they are still dealing with different data sets. Each data set has got its own data model. It's nice, but then when you have to deal with the data, you each have to go to your code and write a different type of code to write a different type of data. This is not the case here. So of course it's not that easy. It means we have to make some compromises sometimes by duplicating some information. But overall, this should really improve the data uptake. I will have to move on now because we are running very short on time. So another thing has to do with data policies. This is an example where data policies have been identified and labeled and organized in one of the contracts. And they have come up with this concept of hierarchy. So ideally, we would like all the data to be free and open. I mean, who doesn't want that, right? The reality is that our world was not constructed like this. Our agencies were not constructed to provide data for free until very recent agencies. So this is why we have different types of data policies that apply to the data. And for now, we cannot just apply different data policies unless they agree. So this, making this obvious is going to help us move from the lower tier, where we have bespoke arrangements with lots of red tape that we cannot redistribute and so on, or commercial applications are not allowed, move slowly towards the first tier. And then the last point about this is that collecting data is very, very difficult. I'm not going to say it's a minefield, but as soon as you're talking about legal aspects of data policy, you have to be very, very careful. So this is one of the contracts is working on. KNMI is doing that in particular, along with other partners from UMetNet over Europe. And they have to deal with many different players. Each of them is coming with different requirements on how they will like the data to be propagated or not. So this time series here at the bottom is showing the number of stations that are available by variable over Europe. And so this is facing some challenges, yes. Another type of rationalization is going to be about what we're doing about reference data. An example is GNSS. GNSS signals global navigation, or GPS, I'll just call it GPS for people who know GPS. It has to do with sending high-frequency radio signals. And those are very nice because they are highly calibrated. But this is serving much more than climate. So we're also looking into discussing with the other communities like geodesy. So an example of data rescue, data from Africa. This is a collection which has been imaged in Belgium. And it's 4 million images, so it's a lot of pages of text and numbers. Sometimes they look as good as in this one, right, left-hand side, and this, believe me, this is a good copy, this one. Although it looks a lot messy, but it's a good copy. But sometimes it's much more black or much more white, or there is a line in the middle and all sorts of stuff. So one of the contracts that look at this has looked at that and come up with a set of recommendations of which data set should actually be digitized. Digitized in the sense of you have to turn this image into numbers with the metadata, with the uncertainties that you have. If your number is not sure, you have to trace this and so on. So this will happen in the next few years of our phase. So to wrap it up is that we have a context which is rapidly changing over Europe. Not just about the uptake of the data, but about how flexible we can be and how much data we can propagate. The key points we had this morning had to do with reaffirming the value of the in-situ data. We had a side meeting, and we really realized that even in a meeting like this, it doesn't hurt to remind that in-situ data is a bit like water, electricity. You think it's always going to be there, but now we know it's not always going to be there unless we keep talking about it and promoting it. Because at some point, there is somebody paying for those instruments and recalibration. So we have to make a key point of reminding whenever we're using this data, these are the data I'm using, and so on. So attribution is very important. The second point has to do with integration, which is what we're going to try to do, and I was very happy to hear this is one of the key aspects of the service. And last point, I invite you to have a look at the posters. The name of the presenters are right here. Thank you.
Thank you very much, Paul. And since there is some time left in your slot, let's see if there's a quick question from the room at this point. Quick question that Paul could perhaps answer in 2 minutes. Okay, so I'm not sure who was first. That's very polite. Mr. Dolman, go ahead.
I take your message from the... I take very much your message of the importance of in-situ data. One of the problems that we have in terms of GCOS is not sort of making the relevance visible of the in-situ data, but getting to the individual observers of in-situ data, which are very scattered all over the place in different small organizations, universities. For meteorological data, it's generally fine because that tends to be well curated, but for a lot of the other data, it's very hard to get to the in-situ data and organize it. How do you think you could contribute to that?
So for this, thank you for this question. It's actually one of the points that has to do with data policy and attribution. There are, we're looking at some data sets where indeed the PIs want to have their names featured. And it's not about their names, it's about the fact that people have contributed this behind them. So what we're looking at now is keeping the traceability to the sources at the lowest level where it makes sense. So this is exactly that. And like this, when you would download the data, you would be able to see the exact source where it's coming from. If we have made that traceability, then we can come up with statistics and say, aha, the data have been used and so on. So then we can maybe feedback some of the fact that those data have been used and so on. I don't know if that answers partially some of your question, but thank you.